A cable consisting of many copper wires is used to transfer electrical energy from a generator to an electric load. The copper wires are protected by an insulator. The copper wires are insulated. The copper wires and insulator are both exposed to an electric field. Discuss with reference to charge carriers why significant electric field only exists in copper wires. So this is a 3-mark question. In order to answer this, you would have to say that um, that when an electric field is applied, you'd have to say when an electric field is applied, electrons, if it accelerates free electrons, and you have to say that electrons are charge carriers, and you have to also state that metals have many free or valence electrons, while insulators do not have any, so do not have free electrons. So that is why, and current is the rate of flow of electrons or charge, which is why metals have significant current, while insulators do not. So the next part to this says that a cable consists of 32 copper wires, each of length 35 kilometers. Each wire has a resistance of 64 ohms. The resistivity of copper is 1.7 times 10 to the power of negative 8 ohm meters. Calculate the radius of each wire. So for this, to calculate the radius, you can use the formula for area of a circle because they are circular. So we go to the formula booklet and we have resistivity of a metal wire, which is resistivity is equal to resistance times area over length. So in other words, you can rewrite this as you can rewrite this as area equals resistivity times length over resistance. So that would be your area, which is equal to 1.7 times 10 to the power of negative 8. So 1.7 times 10 to the power of negative 8. Then times times the length, which is 35 kilometers. So times 35 times 10 to the power of 3 for kilometers over, times, yes, then divided by resistance, which is 64. And what you end up getting is 9.29 tons. So that's the area. So you get 9.3, let's say. 9.3 times 10 to the power of negative 6, 10 to the power of negative 6. So then from this, we know that area is of a circle is equal to pi r squared, pi r squared. So therefore, we can substitute this as r squared is equal to our area, like right here, divided by pi. And we can, to make this the square root, to find r, we can just take the square root of that. So then we have square root of our previous answer divided by pi, which is equal to 0.0017 meters. So 0.0017 meters, two significant figures, since that is what is given to us. You can write this in other forms as well, but I just prefer to keep it this way. And now there's a current of 730 amps in the cable. Show that the power loss in 1 meter of the cable is about 30 watts. So what we can do is, firstly, we find that the resistance of the cable is the resistance of copper wires divided by the number of copper wires. So resistance, or R in this case, is also equal to 64 divided by 32, which is equal to 2. We also have So now we can go back to our formula booklet and find the power dissipated, which is P is equal to VI is equal to I squared R is equal to V squared over I. So let me just put this here. And what we can do from this is we can calculate the power dissipated from the power dissipated from current, which we have here, and we have resistance. So thereby we can use this formula where power is equal to I squared R. Power is equal to I squared R. And since it is in 1 meter, we just divide it by the length, which is 35 kilometers. So 35 times 10 to the power of 3. And what we get here is 730 squared, then times by the resistance, which is 2 ohms, which we've delved into just now, divided by the length, which is 35 kilometers. So that is how we get the approximation of 30.5 watts, which is approximately equal to 30 watts. So then for the last question, when the current is switched on in the cable, the initial rate of rise of temperature of the cable is 35 meter Kelvin per second. Specific heat capacity of copper is 39 joules per Kelvin per kilogram. Calculate the mass of 1 length of a meter. So for this, we can actually use the formula in topic 3, I believe. Q is equal to mc delta T. So in this case, we do know Q. Q was our 30 watts from before. So 30 is equal to mass times by specific heat capacity, which is 390, times delta T, which is 35 megakelvin per second, so 35 millikelvin, so 10 to the power of negative 2, I believe. So if we plug this in, M is equal to 30 divided by 390 times 35, or actually 3.5 times 10 to the negative 2, else you can say 35 times 10 to the power of negative 3. So times 10 to the power of negative 2. And what we get here for the mass is 30 divided by 290 times 3.5 times 10 to the power of negative 2. And you get 2.19, or just 2.2 kilogram.